Hello again. In this video, we're going to begin talking about the material from section 4.3, where we learn that the derivative is a very useful tool when it comes to graphing functions. Now, the reason it's a useful tool for graphing functions is because it tells us three different things about the graph of a function. The first one is it's going to tell us where the function is increasing and decreasing. The second one is it's going to tell us the location of the relative maximums and relative minimums, also known as local maximums and local minimums. And then the third thing that the derivative is going to tell us about the graph of the function is about the concavity of the function. And we'll talk about concavity later on in this section. But for now, we're going to focus in on how the derivative tells us where the function is increasing and decreasing. Okay, so first of all, what does it mean to be an increasing function versus a decreasing function? So a function is said to be increasing if, as you move left to right on the x-axis, the y value of the function increases. And of course, if you move left to right on the x-axis and the y value decreases on the function, then it's a decreasing function. Now here's how the derivative is so useful in determining whether a function is increasing or decreasing at a particular point. Notice that this function is increasing, and if you take the slope of the tangent line at this particular point, the slope of the tangent line is positive. That indicates that the function is increasing at that point. In fact, if you take another point over here and look at the slope of the tangent line, the slope is positive as well, again indicating that the function is increasing at that particular point. Now, if the function happens to be decreasing, then you can see that the slope of the tangent line at a particular point on the function has a negative slope. That's true for any point that you pick on the function, right? Over here, the slope of this tangent line is also negative. So that's how the derivative is going to be useful in determining whether a function is increasing or decreasing at a particular point. We're going to extend this idea to finding out where a function is decreasing or increasing in terms of an interval. Okay, we're going to find the intervals where a function is increasing and where the intervals where a function is decreasing. And so we have a test for that, and that's what theorem 4.7 is about. So here's what the theorem says. It says, suppose f is continuous on an interval I. So we do need the function to be continuous on some interval before we can use this test. We also have to suppose that it's differentiable at every interior point of the interval I. So it needs to be both. It needs to be continuous on the interval, and it needs to be differentiable on all the interior points of the interval. But as long as we have both of those conditions, then if the derivative f prime of x is greater than 0 at all the interior points of I, then f is increasing on the interval I. Whereas if f prime of x is less than 0 at all the interior points of I, then the function is decreasing on the interval I. Okay, so let me show you a problem where we actually apply that test. Okay, so here we have a function, and we want to know on which intervals is the function increasing and decreasing. Okay, so here's how we're going to do this. First of all, we're going to have to take the derivative, right? The test requires us to find the derivative of this function. Let's find the derivative first. Now the derivative of this, of course, is 6x squared plus 6x. Now, at any particular point where the derivative is positive, we know the function is increasing at that point. And any particular x value where the derivative is negative, we know the function is decreasing at that point. But it's kind of ridiculous for us to just continually plug in x values, decide whether the derivative is positive or negative, and therefore the function is increasing or decreasing. because there's just too many x values to plug in. So we're going to be sort of smart about how we do this. What we're actually going to do is we're going to try to determine where the derivative is equal to 0. The reason we're going to do that is because that's the spot where we go from being positive to being negative, where the derivative goes from being positive to being negative. It has to go to 0 first. Okay, so this is like the transition point between being the derivative being positive and being negative. So let's find out for which x values we have this particular transition point. Okay, so to solve this, of course, you just want to factor out that 6x, and that's going to leave you with x plus 1. And then if you solve this, one of these would have to be 0, right, to get a 0 over here. And this would tell us that x is 0, and this, of course, tells us that x would have to be negative 1. So, in other words, there's two x values where the derivative is 0, right? It's 0 when x is 0, and it's 0 when x is negative 1. Now, what we're going to do is we're going to create what's called a sign chart for the first derivative. Okay, so starting at negative infinity, the first place that we have a possible transition from the derivative being positive to negative or vice versa is at negative 1. And then the next spot where that might happen, that transition might happen, is at 0. And then after that, we have no possible transition points. By the way, I guess I should mention this. We also need to check where the derivative is undefined or does not exist, because that could also be a transition point. It could be that your function goes up and down in an abrupt fashion. You can see it's increasing on this side and then decreasing on this side, and that transition occurred when the derivative is 0, undefined, not 0. So we actually need to check both cases. So this is the case when the derivative is 0, and then we need to check the case when the derivative does not exist. Okay, so the case where the derivative is 0 would be a case where you have a smooth transition from like increasing to decreasing, or decreasing to increasing. Likewise, down here you could increase and then decrease in an abrupt fashion. That would be the case where the derivative is undefined. Okay, so let's talk about this second case when the derivative is undefined. So our derivative here is 6x squared plus 6x. And so the question is, for what values of x is it not defined? Well, if you think about it, you can plug any number in for x and you will get a number out for the derivative, and so it exists everywhere. So this never happens. Okay, derivative does not exist. That never happens. Derivative exists for all x values. So that leaves us with only these two. Now, by the way, these are called critical points. Critical points are the points where the derivative is either 0 or doesn't exist. So we're just basically finding the critical points. Now, after you find the critical points, then you go ahead and just plot them on this number line. And then you look at these different intervals. You've got 3 different intervals that you have to look at. And we're going to make a sign chart for each of these intervals. Now, we know in this particular interval, the function is either increasing or decreasing. It's got to be doing one or the other. So what we're going to do is we're going to just pick a test point in here. Pick any point you want in this interval, so like -2, and we're going to plug that into the derivative. Now, when you plug it into the derivative, which is right here, you're going to get 6 times negative 2 squared plus 6 times negative 2. And that's going to give you 24 minus 12, which is 12. So the derivative is positive at this particular point, and that means it's positive for every point in this interval. Okay, and that means the function's increasing in that interval. Okay, now we got to just do that for each of these intervals. So I need to pick a point in here, a test point in here, so maybe negative 1/2. And then we're going to plug that into the derivative again. In fact, I'm going to plug it into here. It's a little bit easier for us to do here. So you plug negative 1/2 in. So you can see here you're going to get negative 3. And then this is a 1/2, right? Positive 1/2. So we get negative 3/2. That means the function's decreasing in this interval. Okay, and now let's just pick a test point in here, like 1. 1 would be a good test point to use here. Plug 1 in, and you can see that you get 12. And that means the function's increasing. Okay, so if we want to just sort of put a cap on this problem, the function's increasing in this interval and in this interval, and it's decreasing in this interval. And then what we're going to do later on is we're going to take this information and use it to help us graph the function. Now let me just show you real quickly the graph of the function just to sort of reinforce what we found. So here's the graph of that function that we were working with. The graph looks like this. And you can see that it's increasing from minus infinity to minus 1. And remember, minus 1 was one of the critical points. And that's where the derivative was 0, right? So that makes sense. And then it was decreasing from negative 1 to 0 in here. So you can see it's decreasing. And then at 0, we got another critical point. And that was because the derivative was 0. Right? The derivative was 0 at negative 1, and it was 0 at 0. These were the smooth transition points, turning points. We didn't have an abrupt turning point, and you can see that in the graph. And that's the reason we didn't get it. We had no critical points in the second case when the derivative does not exist. And finally, you can see that the function does increase from 0 to infinity. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.